So this is the recorded version of our talk, Information-Theoretic Characterization of Vowel Harmony, a cross-linguistic study on word lists, which will be given during the SIGTAP workshop at EACL 2023. So firstly, what is vowel harmony? Vowel harmony is a constraint on the vowels of the word form, meaning that all vowels in a specific word need to agree with respect to a specific feature. Feature can be vagueness, for example, in Finnish, Hungarian, Turkish, Korean, roundedness, Turkish, Mongolian, nasality in Guarani, and tongue position in Mongolian. And vowel harmony mainly surfaces in inflection and derivational morphology, but also in the bare stem forms of a language. Yeah, so here's an example, Turkish front and back harmony. When inflecting a Turkish word for genitive and plural, one has to choose the correct suffix, the correct suffix form. After a back vowel, one has to choose one of the back suffixes, which can also vary based on roundedness, or one of the front suffixes, which can also vary based on roundedness. And for plural, there are only two choices, back and round. So if we have a word like girl, and when inflected for genitive, we just add the respective form of the suffix to the word stem. The same happens for a word with a front vowel. We choose the correct form, front form, and append it to the word stem. Now, if the same word is inflected for plural, the plural suffix intervenes between the stem and the word form and the suffix. But it also has to agree based on backness. So here we have to choose the back form. And for the second word, for face, something more complex happens. First vowel is front, next vowel is plural suffix is in its front form. And the genitive suffix changes in form because this is actually a unrounded vowel, therefore the genitive suffix has also contained an unrounded vowel. Yeah. So now our motivation. In previous work, vowel harmony was mostly quantified based on probability or frequency estimates derived from large corpora of inflected word forms. For example, by Goldsmith, Baker, and Meyer et al. But this specific type of data is not easily acquired. It presupposes that you have at least some large corpus like the Bible or legal texts or whatever. But if you have a really low resource language, this obviously does not work. And therefore our approach was to instead use word lists, which are the most likely thing to be available for any language. And they thought would have the additional advantage that one could also recover a vowel harmony if it's not present in the inflection morphology. At least in this case, our model would be fairer to languages which don't have vowel harmony in the inflection morphology. Because for all languages, we just use lemma forms which are not inflected, maybe derived, but not usually not inflected. Yeah, and we wanted to use a new language model to parameterize the probability distributions we use to measure vowel harmony. This is just a smart way to parameterize a probability distribution. But it allows us to use the same metric to infer these probabilities than we used to quantify vowel harmony, namely surprise, which is the negative logarithmic probability of the vowel or word form given its context. In our case, it's the vowel. In normal neural language processing, it's the word, the rest of the word. Yeah. Now to our data, we use the North-UX dataset, which contains a large diversity of languages from 9 language families. It concept-based word lists for 107 languages. So these word lists contain over 677 to 1513 words per language. They are constructed as follows. In the left-hand column to the left are the concepts. For example, I, no, so all the same for all languages. And then in the rows are the respective word forms representing that concept in some languages. Here, examples are English, German, and Russian. Yeah. So this ensures that the vocabulary or estimates are derived from is the same for all languages. So this also doesn't give you an advantage to specific versions, which might be longer in some languages than in others. So we used a small subsample of the North Julius languages to quantify vowel harmony. We choose 5 vowel harmony languages: Finnish, Hungarian, Manchu, Kaka, Mongolian, and Turkish. Mainly because those are languages in which vowel harmony is strong and relatively easy to recover. And they also have transparent harmony systems that should not be too difficult to model. Kaka Mongolian is kind of an exception to this, as it has 2 types of harmony, which both have neutral vowels. It's far the most complex language in our sample, but the others are kind of straightforward. This table contains the harmonic groups of the different languages. For example, for Turkish, there are minus back, minus round, plus round. And in any word form, the vowels should only be for one of those groups. So only for minus back, minus round, or plus round, but not for any combination of those. So most languages from a sample have neutral vowels. These are vowels that trigger vowel harmony, but don't participate in it. Meaning that, for example, in Finnish, you could have word forms with both plus back and back neutral vowels, although the back neutral vowels are phonologically fronted. But they don't trigger vowel harmony, which means that in this case, disharmonic sequence can happen. Yeah, now to methodology. Our new language model is quite straightforward. It's just a fishbowl LSTM, which takes in the sequence of phonemes. So it takes in the word form as phonemes, and then outputs predictions of the vowels. So in the input, the vocabulary is over the whole phoneme inventory of the language. But in the output, we restricted this to just the vowels, because this is in the input we are interested in. This, of course, has some numerical influence on the numerical values for our surprisal estimates, but yeah, it doesn't really matter, because we would only look into the vowel probabilities anyway. Yeah, so we used the architecture and hyperparameters from Pimentel et al. In 2021. Yeah, and as I said, the task of the neural language model was just to predict the next phoneme, and then the parameters optimized by backpropagation by minimizing negative log likelihood loss, which is basically surprisal. Yeah, and the important part is that we trained one model per language. So this is not a multilingual model. Every language had its own model, and we also trained it until validation loss. So the loss on our validation set converged. Yeah, now to the metrics we used to quantify vowel harmony. First one is very straightforward. We name it phoneme surprisal. It's just the negative logarithmic probability of a specific phoneme given a context. So in a word like sinne, which is Finnish for I locative, or in the eye, at the eye, whatever. After reading in the first 4 phonemes, S, I, L, and M, we would look at the predictions of the neural language model for the next phoneme, which must be a vowel. And then you would obtain the probability distribution, which is shown in the table on the left and the right hand side. These are not actual probabilities, but values that I have made up, just so that you can get the general idea. So in this case, the probability for the harmonic correct vowel is highest. Therefore, it gets a very comparatively low surprise value. Yeah. So, but what you in the end wanted to do is to contrast the probability to encounter a harmonic vowel with the probability to encounter a disharmonic vowel, so one that does not belong to the same harmonic group. And to quantify this, you also calculate the surprise values for the disharmonic vowels. So this happens as a summation over the probabilities of the individual vowels, and then the logarithm, negative logarithm, is taken. So this is not an instance of summing over replacing a product of probabilities with the sum of probabilities by taking the logarithm, but this is really just the sum of the probabilities, and then the logarithm is taken. And this way we obtain two surprise values for the harmonic and disharmonic condition. And in order to quantify how strong the vowel harmony effect in this particular word form, at this particular position is, we simply subtracted the two values from each other. So this is the formula for feature surpriser. It's just a sum. It's just a sum over the, as I said, it's just a sum over the probabilities of the individual phonemes. And then the value that we look at is the difference between the disharmonic and the harmonic surprise values. Yeah. Yeah, so this is the formula that we use to calculate this. It's just what I already said. If the difference between the harmonic and the disharmonic condition is positive, that means it's more surprising to find a disharmonic sequence than a harmonic sequence, then it's an indication, we take it as an indication of a strong vowel harmony constraint. If the difference is close to 0, then harmonic and disharmonic sequences are equally surprising, equally likely. That means that the language doesn't have vowel harmony at all. If this difference is smaller than 0, then vowels with different harmonic groups with different features are dissociated from each other. And this, in theory, should not occur in our sample, but it might occur given that the language has a specific grammar where it's important that the vowels in the word form are dissimilar from each other. Yeah. So now to our results. First, we will look into one individual language, namely Turkish, because here the effect is expectedly strong. The left-hand plot shows surpriser for back harmonic and disharmonic and the disharmonic sequences. Yeah, so surpriser for harmonic sequences is really low. So here, I think here the probability of the back vowels given a previously called back vowel is close to 1. And for the disharmonic condition, it's quite high. The same is true for round harmonic and round disharmonic condition. The harmonic condition has low surpriser, the disharmonic condition has relatively high surpriser. The difference between back harmonic and round harmonic sequences is significant, meaning that back harmony is stronger in Turkish than round harmony. This is a finding that's also supported by the Goldsmith and Wiggle paper for Finnish. Yeah, and on the left hand side, yeah, you see the comparison between the back harmonic, the front harmonic and front disharmonic conditions individually. Yeah. So these are the results for all the languages in our sample. The vowel harmony languages have colored box plots. The non-vowel harmony languages have gray box plots. And as you can already see, the non-vowel harmony languages are all on the left-hand side of the diagram. These are ordered by the mean value, meaning that for those, the difference between harmonic sequences, disharmonic sequences, surprising, is very small, indicating that they don't have vowel harmony. So for some feature combinations, for vowel harmony languages, this difference was also quite small. This has mainly to do with the neutral vowels, which are also in Finnish-Hungarian the most frequent vowels, and they can occur in disharmonic conditions, and it's legitimate from the point of view of the phonology, and therefore the effect shown here is not that strong. But for Turkish, as you see, and also for Manchu, and for some instances of for some features of Kaka-Mongolian, the effect is quite strong. And in all cases, the difference between harmonic and disharmonic forms was significant. Now to discussion. So we've shown that a new language model can learn vowel harmony constraints from word list data, but word lists are also on the larger side. Like the ordinary length of a word list is 100 items. That's the size of the Swedish list. People found some time ago that this is too few and have come up with larger word lists as the one used in Arthur-Lex, but it's not said that for every language such a large corpus is available. So the model found strong vowel harmony constraints in Turkish, Manchu, and Kaka-Mongolian, and to a lesser degree in Finnish and Hungarian, but this is caused mainly by the harmonic vowels. And for Finnish and also for Kaka-Mongolian, for Hungarian and also for Kaka-Mongolian, we encountered the problem that the test set, so which was for every language around of a size of around 300 words, was too small to have many instances of words with 3 or more vowels. And this is necessary to show the effect of neutral vowels. So in this case, the size of the word list was still too small because we have to set aside a large amount of it for training. Yeah. So this is my last slide. It shows how many word forms with 2 vowels and 3 vowels there are in a specific language. So, for example, for Manchu, which is at the top of the plot, we have 1,000 word forms with 2 or more vowels, and 500 word forms with 3 or more vowels, which is sufficient. But it also doesn't have it doesn't have a complicated neutral vowel system. Therefore, yeah, this is expected. But as you can see, most languages have a rather small amount of items with only 3 vowels. And yeah, this becomes a problem when the language also has neutral vowels. And yeah, then in this case, the analysis to be made cannot be conducted. Yeah, this is not only a problem with neutral vowels, but also with vowel harmony constraints, which are maybe not that strong. It may not occur in all the word forms. Therefore, the sample size has to be larger in order to find some instances of them. Yeah, and this can be caused by loan words, which sometimes fall follow vowel harmony constraints, sometimes do not. In Turkish, they mostly do not. And of course, introduce noise to the data, and if the noise is too large, then the test set has to be expanded in order to account for that. Yeah. So this partially supports the claim of Docker et al. From 2019 that word lists for this kind of typological analysis have to be larger than roughly 400 word forms. So for some languages this might work out. For some languages it doesn't work out. In our case, 400 word forms is too few for some languages, for Manchu, Kaka-Mongolian, Finnish-Ugarian, definitely. But for Turkish and part for Kaka-Mongolian, it was enough. Yeah, so then thank you for listening to the pre-recorded presentation, and goodbye.